Welcome to the second keynote talk of today. It's my pleasure to introduce Maria-Florina or Nina Balcan. She's originally from Romania and now at Carnegie Mellon University, where she's a Microsoft Faculty Fellow and Sloan Fellow. She's interested in machine learning, artificial intelligence, and theoretical computer science. She has received an impressive number of awards, especially in recent years, including Grace Hopper and awards from Amazon, Bloomberg, and several others. She has chaired or co-chaired several top-level conferences like COLT, ICML, NeurIPS, Fox workshops. She will be the general chair of ICML this year. And okay, I think it will be a very interesting keynote talk.
Hello. I would like to start by thanking the organizers for inviting me. It is a pleasure to be a speaker at the Latin conference. My talk today will be about using machine learning for data-driven algorithm design, and more specifically about, I'll talk about some recent theoretical guarantees we have been developing in order to help put this very exciting area of data-driven algorithm design on solid theoretical foundations. And my focus here will be on discrete optimization problems or combinatorial algorithms for discrete structures. So this is really using machine learning and learning theory to influence theory of computing, algorithm design, and many of the corresponding application areas. And let me start with a high-level overview of this line of work. So the classic way to analyze and design algorithms for combinatorial problems assumes that the algorithm that we design for the given problem will be used to solve worst-case instances of the problem about which the algorithm has absolutely no information at all. And the typical performance guarantees we seek for within the classic analysis framework impose that the algorithm that we design for the given problem must succeed even for solving a one-time, one-shot, worst-case instance of the underlying algorithmic problem. Now, within this classic analysis framework, there are certain types of problems that are easy, in the sense that for this, we have optimal algorithms with desired performance guarantees. So, for example, if we care about running time as our major performance measure, we have optimal polynomial time algorithms that are guaranteed to output the optimal solution in polynomial time, even for worst-case instances. And examples of such easy problems include basic problems like sorting and shortest paths that we teach in our basic undergraduate algorithms courses. And again, for this, we have optimal polynomial time algorithms that are guaranteed to output the optimal solution in polynomial time, even for worst-case instances. So certain types of problems are easy within the classic analysis framework. However, we also have many problems for which we do not have such strong performance guarantees. And examples of such hard problems include various partitioning problems over graphs, clustering problems, subset selection problems, pricing problems, and so on. And in fact, really most combinatorial problems are hard within the classic analysis frameworks. Now, an interesting approach commonly used in practice for attacking such hard problems, especially in cases where you need to solve not only one instance of the underlying algorithmic problem, but we need to repeatedly solve instances of the same algorithmic problem. So an interesting approach to attack such hard problems is to use machine learning in order to automate the algorithm selection or the algorithm design. And this is what I call data-driven algorithm design. And the basic idea here is that for such hard problems, in practice, different methods work better in different settings. And also, in practice, we also often have a large family of methods that we could try to use. So naturally, given a specific application or a specific domain that we care about, we could hope to use machine learning and instances of the problems coming from our specific application or from our specific domain in order to select an algorithm that does well on our type of instances coming from our specific domain. Now, this approach has a long history in several communities. For example, it has been used for a long time in the artificial intelligence community, also in the computational biology community, and indeed several empirical breakthroughs have been produced through this approach. So this is, has been very exciting from a practical point of view and empirical point of view, but quite surprisingly, up until very recently, there have been basically very little or almost no theoretical guarantees for data-driven algorithm design. And in my talk today, I'll tell you about recent work in my group with my students and our collaborators on providing strong, provable, strong theoretical guarantees for data-driven algorithms. And we looked at a variety of case studies of widely used families of algorithms that are used for solving a variety of problems appearing in or relevant to many different fields. So for example, we consider clustering problems relevant to data science, sequence alignment problems relevant to computational biology, and pricing problems relevant to algorithmic game theory and computational economics. And the interesting fact is that when we use learning theoretic perspectives to provide provable guarantees for data-driven algorithms in this context, we discover structures that are much more delicate and much more complex than typical structures that we analyzed in classic machine learning and learning theory. And so to provide strong provable guarantees for data-driven algorithms, both for the statistical learning formalization and for the online learning formalization, we had to develop new analysis techniques. And overall, this line of work pushes both the boundaries of algorithm design, because now we have provable guarantees for data-driven algorithms, but also the boundaries of machine learning and learning theory. And I'll tell you about some of these, the major insights from this line of work today. And I'll start by talking about how we can formalize data-driven algorithm design by using statistical learning theory. But before doing so, just to be concrete, I want to give you a concrete example of a combinatorial problem that we might want to solve in the data-driven way. And this is clustering. Where we are given as input a set of objects, say news articles, web pages, search results, and our goal is to organize them as well as we can into natural groups. And notice that clustering is an example of a problem that we might need to solve repeatedly. So for example, if we are using clustering to cluster news articles, which is what Google News does, we might need to cluster, we often need to cluster news articles every day, in fact, many times a day. Now, a bit more formally, in order to talk technically about the clustering problem, we could, for example, formalize it by using objective-based clustering, where we pick a specific objective function, like k-means, and try to optimize it. And to remind you, for the k-means clustering problem, we have as input a set S of n objects and the distance function between pairs of input points or input objects. And then the goal is to output a set of, to output a partition of the input set of points and centers for each part of the partition in order to minimize the sum of all points of the distance squared to the nearest center. So this is k-means clustering. We could also consider the related k-median clustering objective or the k-center clustering objective. All of these objectives and other objectives as well are, however, can be hard to optimize, meaning there is no we cannot hope to find the polynomial time algorithm that will do well on worst case instances. And so it makes sense to try to address them in a data-driven way. Or we could also consider a machine learning or unsupervised learning formalization of the clustering problem, where we assume that there is a true unknown ground of clustering of the input set of points, and we are trying to recover it to get as close as we can to it. And this formalization is also hard, so it also makes sense to use a data-driven approach to attack this problem. Now, with this concrete example, I can now describe how we can think about data-driven algorithm design as a statistical learning problem. So what we do, we first fix the problem that we want to solve, and this could be, for example, k-means clustering. And then what we do, we fix a family of algorithms, and this can either be a family of algorithms that is commonly used in practice for these problems, or it's maybe we might have analytical reasons to believe that algorithms from that family will do well on our type of instances. Then what we do, we take a sample of typical instances coming from our specific application or from our specific domain, and technically we'll assume that these instances are drawn IID, that means independently, identically distributed from some fixed but unknown distribution of our typical instances. And then the goal is to use this sample of typical instances to find an algorithm from our family of algorithms that will do well on new instances coming from the same distribution of our typical instances as a training set of typical instances. So again, we fix a combinatorial problem that we want to solve. Then we fix a large family of algorithms for our problem. And these algorithms could have our favorite types of components, like greedy components or dynamic programming components. And this family of algorithms could even be infinite, since some of these components might have pre-evaluated parameters or knobs that we can hope to tune. Then we take a sample of typical inputs or typical instances coming from our specific domain. So for example, if we're trying to solve a clustering problem, say we're trying to cluster documents by topic, then these typical instances will be subsets of documents. So here is typical instance 1 will be a first set of documents, typical instance 2 will be a second set of documents, and so on. Typical instance n will be another set of documents that we might want to cluster. And these inputs can either be unlabeled if we're trying to solve the k-means clustering problem, or they could be labeled if we're trying to get close to the ground truth, so if we're using more machine learning formulation. Or as another example, if we're trying to solve like a graph-based facility location problem, then these typical instances will then be typical examples of graphs coming from our specific application or domain. So we take this sample of typical inputs for our algorithmic problem coming from our specific domain, and we use it to find an algorithm from our family that we want to prove does well on new instances coming from the same underlying distribution of our typical instances. Now, this is really a very natural statistical or distributional learning formalization of data-driven algorithm design. And so a natural way to try to attack it is to do ERM, what we call in machine learning ERM, or empirical risk minimization, meaning what we do is we'll try to find an algorithm ahead from our fixed family of algorithms that is nearly optimal or maybe nearly optimal on average over the training set of typical instances. This makes a lot of sense, of course, but the key question is, will this algorithm ahead do well on new instances that we have not seen in the training set? So, for instance, for the clustering problem, the algorithm ahead that we output, of course, will do well on the training set of typical instances because we have chosen it to do so. But the key question is whether it will do well on new instances that we have never seen in the training set. Now, the answer to this question will depend on how many typical instances we have seen in the training set. And so a very important question here is this sample complexity question, which asks, how large should our sample of typical instances be in order to guarantee that good performance over the training set of typical instances translates to good performance on new instances as well? Now, we can use tools from statistical learning theory to address this sample complexity question. And in particular, one tool that we used a lot in our work is uniform convergence. And informally speaking, these uniform convergence bounds are bounds on the number of training samples we need to see in the training phase in order to guarantee that with high probability over the draw of the training set of typical instances, we have it uniformly for all the algorithms in our family of algorithms. We have it for any such algorithm, its average performance over the training set of typical instances is close, say additively epsilon close to its expected performance on a new instance coming at random from the same distribution over typical instances as a training set of typical instances. And these uniform convergence bounds are great because if you think about it, once we have uniform convergence, then this immediately implies that the algorithm may head. So if we have enough samples to achieve uniform convergence, this then implies that the algorithm may head that is nearly optimal over the training set of typical instances also has high expected performance. And in particular, it will do nearly as well as the best algorithm from the fixed family of algorithms with respect to the fixed unknown distribution of our typical instances. And we know from statistical learning theory that the number of samples needed to achieve uniform convergence, say the number of samples needed to achieve epsilon uniform convergence, is about the intrinsic complexity of the family of algorithms over epsilon squared. Where this intrinsic complexity of the family of algorithms is a learning theoretic notion of complexity, but at a high level is trying to capture the ability of the functions or in the function class induced by our family of algorithms and the corresponding performance measure. So it captures the ability of this family of functions to fit complex patterns. Because intuitively speaking, the more complex patterns we can fit, the more examples we need to generalize and to not overfit. And there are several notions of dimension that we can try to use here that are learning theoretic notions of dimensions. The one that we use a lot in our work is called pseudo-dimension, which I'll mention later in the talk. So we can use tools from statistical learning theory to analyze sample complexity questions. Now, the key challenge that arises in this context is that the corresponding loss functions or scoring functions now can have many sharp discontinuities on many instances. Why? Because we are trying to solve combinatorial problems that have combinatorial inputs and combinatorial outputs, and we are learning algorithms that have combinatorial modules that are interrelated. And so we can get easily into situations where nearby algorithms will really have kind of very different behavior on many different inputs. And so this is a major key challenge that we have to overcome. And the second key challenge that we have to overcome is that we want the overall process to be computationally efficient. We are able to overcome this in our these challenges in our work for several interesting cases. But before mentioning our work, I want to acknowledge that the idea of using statistical learning or distributional learning to analyze data-driven algorithms was first proposed by Rishi Gupta and Tim Roughgarden in an ITCS 2016 paper. In this paper, they proposed a model, and they also analyzed parametrized families of greedy procedures for subset selection problems. And I found this work really fascinating, and following it and inspiring. And following it, we analyzed many new algorithms classes applicable for a wide range of algorithmic problems, such as clustering problems, partitioning problems, alignment problems. And in addition to these specific case studies, concrete case studies, we also developed general tools for analyzing sample complexity of data-driven algorithms based on properties of the corresponding scoring functions, which or loss functions. And in this case, there will be these dual functions that I'm gonna define later. And we have several papers in this direction for thinking about data-driven algorithms in the distributional learning framework. I'm mentioning these papers on this slide, on this slide here, and also I will give some of the major insights from some of his papers in the next part of my talk. And for each major segment, I'll reference the relevant paper so that you can look at it. And I'll start by talking about the concrete case study for clustering problems. In order to think about clustering problems in a data-driven way, the very first thing that we have to do is to specify a family of clustering procedures we are searching over. And in our very first work in this direction, we considered a widely used family of two-stage clustering procedures, where we first do a simple greedy linkage bottom-up procedure to organize the data into a hierarchy or tree of clusters. And then in a second step, we use a fixed algorithm like dynamic programming procedure to extract the best pruning according to the desired objective from this hierarchy. And so to output a partition or a clustering of the original set of points. Now, both of these steps can be done in polynomial time. This is why this type of algorithms are widely used in practice. And to be a little bit more concrete, what are these bottom-up procedures or linkage-based procedures that we use in the first step? They are very simple linkage procedures where we start with each input point from the original data set of points. So we start with such each input point in its own little cluster. And then we repeatedly merge the two closest clusters until we get a complete hierarchy. Now, different definitions of closest will lead to different clustering procedures. So for instance, if we define the distance between two sets A and B as being as a minimum distance between point X and X prime in the two corresponding sets A and B, then we obtain the classic single linkage procedure. If we instead define the distance between two sets A and B as being the maximum distance between points in the two corresponding sets A and B, we obtain the classic complete linkage procedure. Or if we define the distance between sets A and B as being the average distance between points in the corresponding sets, we get the classic average linkage procedures. And in fact, we can even put down an infinite parametric family of procedures interpolating between these classic procedures, getting a whole spectrum of algorithms. And one such family that we define in our work is what we call alpha-weighted linkage, where we interpolate linearly between single and complete linkage according to a known parameter alpha, according to an unknown parameter alpha that we can try to tune based on data. Okay, and in particular, for a fixed value of alpha, we define the distance parameterized by alpha between two sets A and B as being alpha times the distance given by the complete linkage criteria plus 1 minus alpha times the distance given by the single linkage criteria. In other words, we define the distance parameterized by alpha between sets A and B as being alpha times the maximum distance between the points in the corresponding sets A and B plus 1 minus alpha times the minimum distance between points in the two sets A and B. And then we get this infinite family of alpha-weighted linkage procedures, and we can try to use data to learn alpha. Now, of course, using this alpha-weighted linkage procedure followed by a fixed post-processing like dynamic programming, we get an infinite family of clustering algorithms. Now, what we are able to show in our work, and in particular in our first called paper in this direction, we are able to show that even if this family of algorithms is infinite, the intrinsic learning theoretic complexity is only logarithmic in n, where n is an upper bound on the number of input points. And this is interesting because this immediately implies that we only need quite a small sample complexity in order to generalize and to do well on new input instances that we have not seen in the training set. And moreover, we are also able to show that the overall procedure is polynomial time. Now, the key challenge in showing this result is that it turns out that even for this specific case, we can be in situations where small changes to the parameter, to the alpha-weighted linkage procedure, can lead to radical changes in the tree and final clustering produced. Why? Because if you think about it, a single change to an early decision made by the linkage procedure can really snowball and produce much larger changes later on. So to show that the intrinsic complexity of this family of procedures is not too large, we had to identify a useful structural result. And what this structural result says the following. If we fix a clustering instance of at most endpoints and vary the parameter alpha of the alpha-weighted linkage family of linkage procedures, there will be at most n to the 8 switching points where the behavior or the cluster T produced on that instance changes. So if you think about it, for a fixed value of alpha, when we apply alpha-weighted linkage, we're going to do a sequence of merges and obtain a certain cluster tree. Now, if we change the value of alpha to say alpha prime, we will get a different sequence of merges and get a different cluster tree. What this key fact says is the following interesting fact. It says that if we fix a clustering instance of at most endpoints and vary the parameter alpha over all its range, there will be at most n to the 8 switching points where the behavior or the cluster tree produced on that instance changes. Okay, and what this really implies is that for the overall family of two-stage clustering procedures, is that the cost function is a piecewise constant function with at most n to the 8 pieces. And this is because the second stage is just, we apply just a fixed algorithm on the top of the cluster T produced from the first stage. Okay, in order to prove this key fact, the key idea, without going into lots of details, but the key idea is the following. Imagine that we fix alpha, and imagine that we run the alpha-weighted linkage procedure. And imagine that our alpha-weighted linkage procedure has to make a decision at some point. Should it merge clusters N1 and N2 or clusters N3 and N4? Now, the decision on whether to merge clusters N1 and N2 versus N3 and N4 depends on 8 points. And in particular, depends on P and Q, the farthest away points in N1 and N2, and R and S, the farthest away points in N3 and N4, and on P prime and Q prime, the closest points in N1 and N2, and R prime and S prime, the closest points in N3 and N4. And in particular, the decision whether to merge N1 and N2 versus N3 and N4 really depends on which of these two quantities, alpha times the distance between P and Q, plus 1 minus alpha times the distance between P prime and Q prime, or alpha times the distance between R and S, plus 1 minus alpha times the distance between R prime and S prime is smaller or bigger. And this then implies that an interval boundary where the behavior on that instant changes, or output a different cluster tree, such an interval boundary really must correspond to a root for a linear equality given by 8 points. So it corresponds to a root for a linear equality of the form alpha times the distance between P and Q, plus 1 minus alpha times the distance between P prime and Q prime, equals alpha times the distance between R and S, plus 1 minus alpha times the distance between R prime and S prime. And this then immediately implies that we can have at most n to the 8 interval boundaries and at most order n to the 8 possible cluster trees produced on that instance. Now, this key fact tells us about the behavior of the family of alpha-weighted linkage procedures and the family of the overall, the behavior of the overall family of two-stage two-stage clustering algorithms on one instance. But in order to analyze the intrinsic complexity or the pseudo-dimension of the overall family of clustering procedures, we need to understand the behavior of this family of procedures over M clustering instances. Now, if we have M clustering instances but most endpoints, the immediate key fact, so the key fact on the previous slide, immediately implies that we can have at most M times n to the 8 patterns in terms of the possible cluster trees produced after the first step on these M instances. And now to finish the proof, really all we have to know is that formally what the pseudo dimension is, the pseudo dimension of a family function is the largest number M for which an exponential number of behaviors or patterns is achievable on those instances. And so to compute the pseudo-dimension for our family of clustering procedures, we need to find the largest number of M for the largest number of instances M, for which on one hand, an exponential number of patterns is achievable. So we have 2 to the M patterns achievable. But on the other hand, we know from our key facts that at most M times N to the power of 8 possible behaviors is achievable by using procedures from our fixed family of clustering procedures. And so to compute the pseudo-dimension or the interesting complexity of this family of two-stage clustering procedures, what we have to do is to solve for the largest value of M, for which 2 to the M is upper bounded by M times N to the 8. And when solving for this, we get that the overall, the pseudo-dimension of this family of procedures is at most log N. From our uniform convergence tools in learning theory, this then immediately implies that we need only log N over epsilon squared samples to achieve, in order to output an algorithm that is epsilon close to the best algorithm from the family with respect to the fixed unknown distribution. And we also, from the structure result that I mentioned, we also immediately get that given a sample S of typical instances, we can find the best algorithm from our family of algorithms on the best algorithm on average over the set of typical instances from our family of algorithms. We can find it in polynomial time. So all we have to do is, given our sample S of typical instances, we just need to find the relevant alpha intervals over the union of these typical instances, and then to find the alpha interval that has the smallest empirical cost on average over the typical instances. Now, an interesting generalization of this result is one where we are trying to learn not only the linkage criteria, but also the distance function between input pairs of points. And this is something that we consider in our most recent iClear 2020 paper on the topic. And this is motivated by the fact that in certain applications, we have very different types of distance metrics that we might want to consider. So for example, if we are trying to cluster captioned images, then we would have a distance d0 based on the image information or based on the pixel information in the image, and the distance d1 based on the caption itself. And so given such a scenario where we have two input-based distance functions between pairs of points, we can now define a parametric family of distance functions where we can use, say, the parameter beta to interpolate between the base distance functions in a linear way, in the way that I have written on my slide. And now we can define a parametrized family of alpha beta weighted linkage algorithms where we use the parameter alpha in order to interpolate between the classic single linkage and complete linkage criteria, and the parameter beta to interpolate between the two base metrics. Okay, so basically here, really intuitively speaking, we are trying to learn both the linkage criteria and the distance function. And both of these are linear interpolations of classic linkage criteria and classic distance and base distance functions. Now, in our work, we are able to show that, again, the pseudo dimension of the alpha beta weighted linkage procedures is only log n, so it's small, which immediately implies small sample complexity to obtain good generalization, which is great news. And without going into details, I want to mention that the key fact in order to prove this pseudo-dimensional result is, again, a fact about the structure of these scoring functions, or I'll call them dual functions. What we do, we fix an instance of at most n points, and what we do, we vary the parameters, the parameters of the underlying algorithmic family. In this case, we vary alpha and beta. And what we can show for this alpha beta weighted linkage is that if we fix a specific clustering parameter we want to solve with at most n input points, and then if we vary the parameters alpha and beta, we can partition the parameter space now with not too many quadratic equations. So we can partition the parameter space with at most n to the 8 quadratic equations, such that within each region or within each part given by these boundary functions, we get the same cluster tree. So really, another way to state this is that if we fix an instance with most endpoints and vary the parameters alpha and beta, kind of the final corresponding cost functions is piecewise constant. Right, so this dual function now is piecewise constant with at most n to the 8 pieces. It's piecewise constant with a number of pieces induced by at most n to the 8 boundaries, and in inside each piece given by these boundaries, the cost is constant. So this fact is crucial for proving our sample complexity result, and also is crucial for getting an efficient implementation for the overall process. And we actually use it to then also show in this work, we also use it to show that we can get clustering algorithms that have significant improvement in practice over standard data sets compared to algorithms like where we don't do any learning, we just apply classic procedures. So this is, I think, very exciting because it shows, it's an example of a result where we are able to get not only very strong provable guarantees on data-driven algorithms, but we are also able to use our theoretical insights to design even better algorithms in practice. I want to mention one more example of a problem, of a combinatorial problem that we looked at, and we try to analyze it in, using statistical learning theory. And this is trying to solve, and here we are looking at partitioning problems that can be written as integer quadratic programs. So in particular, imagine that A is an input matrix, and here we're trying to maximize this quadratic form, x transpose AX, subject to having X having input, a binary input. Okay, so for example, the classic max cut problem, where we are trying to, where we have this input, a graph G, and we are trying to partition the graph, the vertices of the graph into two pieces in order to maximize the weight of the edges crossing the partition. So this max cut problem can be written as an integer quadratic program. Now, as you probably know, max cut and other problems that can be written as integer quadratic programs are NP-hard. And so it makes sense to try to solve such problems in a data-driven way. And to do so, we have to specify a family of procedures that we are trying to learn over. And in our work, we consider a parametric family of procedures where we first do semi-definite programming, a semi-definite programming relaxation of the problem, and then we do a parametrized round on the top of that. And this family is interesting because it includes classic algorithms like the Gomez-Williamson algorithm, but is the best known algorithm for the algorithm that gives us the best known approximation guarantees for worst case instances for the max cut problem. So this family of algorithms that we consider includes the classic Gomez-Williamson algorithm, but moreover, it's also known that for certain distribution over, for certain types of graphs, we might want to use a specific family, certain types of algorithms from the family versus other types of algorithms from the family. So it makes sense to try to, so it's known that for certain types of instances, we might want to use certain types of algorithms from the family and not others. But in our work, we are able to show how to learn those algorithms, the best algorithms for a given distribution over instances. And in particular, we're again able to analyze the sample complexity of learning over this family of algorithms. We are able to more specifically show that the pseudo dimension of this family of algorithms is again log n. And without going into any detail, I want to just mention that again, the key fact to show this pseudo dimension result is a structure result about these dual functions. Where we fix an instance of the problem, in this case, we fix an instance of the max cut problem, and we vary the parameter S of the underlying family of rounding procedures. And now we are able to show that the corresponding cost function, this dual function, is now piecewise inversely quadratic. So it's not piecewise constant like in the previous two examples, but is piecewise inversely quadratic. And we can again bound the number of pieces. We are able to show it's only n plus 1 pieces. Okay, and this is crucial to getting the sample complexity result. Now, similar structure results have been crucial for analyzing other families of algorithms, very different families of algorithms. So for instance, for analyzing parameterized families of dynamic programming procedures for sequence alignment problems, or for analyzing parameterized families of branch and bound algorithms for solving mixed integer programs, which is something that people do often in AI, in artificial intelligence. Or similar structure results were crucial for analyzing parameterized families of pricing mechanisms and auctions and randomized mechanisms for revenue maximization. In all of these cases, what we are able to show is that we have a structure result of the form if we fix an instance of the problem and vary the parameters of the underlying algorithmic family. By the way, these parameters can be multidimensional. So we are able to show that if we fix an instance of the problem and vary the parameters of the underlying algorithmic family, we can partition the parameter space with some nice boundary functions, such that inside each of the piece given by these boundary functions, the final cost function is structured, has a specific form. Okay, so such structure results have been crucial for each concrete case study that I mentioned earlier. Now, in our most recent work, we are able to show, we write a general theorem which says if for your data-driven algorithm configuration problem, you have such a structure result, then we can give you a direct bound on the pseudo dimension. We can tell you how many samples we need to generalize. So this result really kind of decouples the structure result needed for analyzing the data-driven algorithm design problem from the more learning theoretic result, which is once you have the structure result, how many samples you need to generalize. And it's nice because not only it recovers the sample complexity of all the previous case studies that I mentioned earlier, once you have the structure result, but also gives a general recipe from how we should analyze the sample complexity of other new data-driven algorithm design problems that you might want to analyze. Okay, so it's a nice general abstraction. But this is all for analyzing sample complexity of data-driven algorithm design for the distributional learning or statistical learning formalization, where we assume that all the training set of typical instances are given to us upfront in a batch, and that all instances drawn IID from some fixed unknown distribution of our typical instances. Okay, but what if the typical instances come online? Okay, then we have to think about data-driven algorithm design as an online learning problem. All right, and this is what we've been doing in our recent work. So instead of assuming that the collection of typical instances are given to us up front and they are all IID, we are analyzing this online data-driven algorithm selection. We're analyzing the scenario where the typical instances are coming one by one, and they might be adversarially chosen. Now, what we can hope to achieve in this case, the performance guarantee that we can hope to achieve is low regret or no regret. That means we want to show that our cumulative performance, the cumulative performance of our overall learning procedure is comparable to the performance of the best parameter setting or the performance of the best algorithm in hindsight. And we can hope to use tools from online learning theory in order to analyze, in order to try to achieve low regret or no regret for the online algorithm selection problem. Now, the key challenge that appears on trying to do so is that our scoring functions, our dual functions that I talked about earlier, in the data-driven algorithm design context, they are very non-structured, they are not convex, and moreover, they have many sharp discontinuities. And this is a major challenge because classic online learning theory looks at much more structured cost functions like convex or concave. And so, and moreover, it's also known that if the cost functions have sharp discontinuities, we might not be able to achieve no regret on worst case instances. Now, the major contribution of our work in this direction, that includes a series of 3 papers that I have referenced here on the slide. So our major contribution is to identify sufficient condition about the structure of our cost functions or our dual functions. We identify these general sufficient conditions that are sufficient to achieve no regret for online learning, for online algorithm selection. And intuitively speaking, the condition that we provide is what we call dispersion. And intuitively speaking, or pictorially speaking, what this condition requires is that the discontinuities or the sharp transition boundaries of our dual functions or cost functions or scoring functions. So these transition boundaries of our dual functions should be dispersed. So more specifically, we say that a sequence of scoring functions or dual functions for the data-driven algorithm design, they are dispersed if in any ball of radius W, at most k of the functions have discontinuities or have boundaries in those balls. So for one dimension, we really says the discontinuities of our cost functions should not be too concentrated in any small interval. So in our work, including in our Fox 2018 paper and in our UA 2020 paper, we are able to show that if the cost functions or the scoring functions or the dual functions for the data-driven algorithm design context, if they are dispersed, then we can get regret, that is scales like square root of t times b times function of the problem, or t is a time horizon. So this is great because that means that on average the regret per time step goes to 0 as t goes to infinity. And not only were I able to show no regret guarantees, but we're also able to provide a general recipe for analyzing dispersion, for analyzing when we can guarantee dispersion in the case where the input instances are a little bit small. So they are not really worst case, but they have some randomness in them. And in order to provide this general recipe for analyzing dispersion, at the high level and pictorially speaking, intuitively speaking, the key insight is that for these dual functions, we have very often nice structure. And in particular, we've already seen in the first part of the talk that these dual functions often they are piecewise structured. So if you fix an instance and vary the parameters of the underlying algorithmic family, we can partition the parameter space with some boundary functions such that inside each of the p's, the original cost function is structured, is a specific form. Now the additional insight for analyzing dispersion here is that these boundary functions are often algebraic curves. They are zero sets of multivariate polynomials. And using this fact together with insights from algebraic geometry and learning theory, we are able to provide this general recipe for analyzing dispersion for cases when input instances are smooth. And we also provide several application examples for this analysis. More specifically, for example, we are able to show that to provide sufficient conditions for when the alpha beta weighted linkage family of clustering procedures, where we are trying to learn both the linkage criteria and the distance function. So we provide sufficient conditions on the input instances for which this corresponding family of procedures leads to dispersed discontinuities for these dual functions. All right, so to summarize, in this work, we provide strong performance guarantees for data-driven algorithm design for combinatorial problems. And to provide our guarantees, we provide new structural properties about the corresponding dual class of functions, where what we do, we fix an instance and vary the parameters of the underlying algorithmic family. So what we show that these dual functions, they are sufficiently structured, and then we exploit these structural properties to then provide generalization guarantees, sample complexity guarantees for the case when we think about data-driven algorithm design as a statistical learning problem, and we also provide no regret guarantees for the case when we think about data-driven algorithm design as an online learning problem. And because these dual functions, they do have many sharp transition boundaries, even if they are somewhat structured. They are much, and because they are much more challenging than the type of loss functions we typically see in machine learning, the corresponding techniques are also of independent interest. They really should be of interest to learning theory more broadly, beyond data-driven algorithm design. Now, there are many exciting open questions in this direction. I just want to mention a couple. It will be very interesting to analyze other learning models, learning theoretic models for modeling data-driven algorithm design. as a learning problem. So for instance, we might want to consider domain adaptation, where we assume that the test distribution, the distribution from which the test instances are coming, is different from the training distribution from which the training set of typical instances are coming. So this can be more realistic. We can also consider reinforcement learning, where we are aiming to learn state-based decision policies that use the current state of the algorithm to determine how to proceed next. And this, of course, can lead to even more performing algorithms than what they can currently do, better results. It will also be very interesting to consider learning within a single problem instance as opposed to learning across instances. So in what I talked about today, I assume that I have a training set of typical instances, both for the distributional learning formalization and for the online learning formalization. I assume that I have a sufficiently large training set of typical instances. But what if we only have one instance of the problem and we still want to somehow do learning, to learn the best algorithm from the family, from a family of algorithms for our single learning problem instance, for our single problem instance? What if we have a single problem instance and we are trying to learn the best algorithm from the family for the single problem instance? What can we say? Turns out that there has been some empirical work in actually both of these directions, but no formal guarantees yet. And I think this is very exciting and very interesting to try to think about what type of formal guarantees we can provide in these scenarios. And of course, we should also be analyzing other widely used families of algorithmic paradigms for other combinatorial problems. So I think this is a very, very interesting direction, and it has many exciting open questions. And I'm very happy to take any questions you might have. Thank you.
Okay, thank you, Nina. That was really very interesting talk. Okay, it's time for questions now. Anybody?
I have one question.
Go ahead.
How do you know if you've chosen the wrong family of algorithms for your unknown distribution? Is there any way of figuring that out while training? For example, if tuning a parameter is taking a long time, then you know maybe this family was the wrong family?
Yeah, it's a good question. So first of all, I guess maybe I want to mention something that, this framework applies to many different types of performance measures. Like, it could be that you are trying to find the fast algorithm, or it could be that you are trying to find an algorithm that produces a good solution quality, right? So for example, the examples for the clustering problems that I gave, right, for where you do linkage procedures for open programming, there the families of algorithms are polynomial time by design, but we're trying to really optimize for solution quality. So we're trying to find an algorithm that has good clustering quality, right? In another example that I didn't go into detail in this talk, there we're looking at branch and bound techniques for solving mixed integer programs. There we put down families of algorithms that are, these branch and bound techniques, they solve the problem to optimality, the original problem to optimality, but they might take exponential time. So really there, when we're learning, we are trying to optimize for an algorithm that has a small running time. So the loss function is running time in that case, right? So, right. And to go to your question, how do we know? So basically we fix a problem that we want to solve, like we fix a family of algorithms, right? And then we also fix, of course, a performance measure, and we are trying to find the best algorithm from the family with respect to our performance measure, right? Which can be, say, solution quality or running time. Now, how do we know if the family of algorithms that we put down is a good family of algorithms? That's an excellent question. And, it's related, I guess, to like a question in machine learning. How do you know if the family of functions you put down is a good family of functions for your learning problem?
Right.
Right. And so let me just make a couple of remarks. So first of all, like when you put down your family of algorithms for a desired performance measure, so if, you could always put kind of the algorithm that that has the best worst case guarantees, right? Worst case performance guarantees, right? Like for example, if you are lucky, so that for your given problem, for your performance, right, say clustering, so you're trying to do k-means clustering, right? And you can always augment the family. You can always put in your family of algorithms the best known algorithm for clustering for your desired performance measure. Like if you're doing k-means clustering, you can put down in the family the best known algorithm for the best known approximation algorithm for k-means clustering, for instance, right? So that's one thing you can kind of have some sort of safety guarantee there, like, you do, yeah, you can kind of do as well as the best known worst case algorithm with the
right.
instances. Right, can you do something more? Well, it's a good question. So in principle, you could do something more, but it's not necessarily very practical yet. You can do something called structural risk minimization. Like you can keep augmenting, in the talk today, I kind of assume that I have a fixed family of algorithms and I'm optimizing over the best algorithm from the family. I'm trying to algorithms from the family for my type of instances. But you can put down a sequence of algorithms families that are increasing in complexity.
Right, and learn the family basically.
And learn exactly what's the best family, right? Learn the family simultaneously to try, right? But of course, what do you mean by learning the family, right?
Yeah.
Well, there is a language in learning theory for what you can do there, right? You can kind of, given the fixed set of training instances, you can kind of learn the best family that is justified for that fixed set of training instances, right? Because the more complex the family, so you have this hierarchy of families of algorithms, and the more complex the specific family of algorithm is, the more training samples you need to not overfit, right?
Right.
But the more complex the family of algorithm is, the more likely is that you're gonna get a better algorithm, right, for your distribution. And so really that's a question, what's the right level of complexity for what's the right family of algorithms you should be using? Well, you have to balance these two facts, right? But on one hand, you need more training samples. If the more complex the family of algorithm is, that's one fact. But on the other hand, the more complex the family of algorithm is, the more likely is that you're gonna have a good algorithm in the family, right? And there is a technique in learning theory called structural risk minimization that kind of allows you to kind of trade off these two important facts. If you can put down a kind of like a nested hierarchy of families of algorithms, you can kind of learn what's the right family of algorithms in a certain sense.
All right, thank you.
Okay, I think we have time for maybe one more question.
May I ask?
Yes, Eduardo, go ahead.
Hi, thank you. I was turning on my video. So congratulations for the talk. It's maybe I missed something, but I would like to know about in the examples. One of the examples, there was a parameter that you were trying to optimize in the clustering. Yeah. And in the other one, there was the parameter and the distance.
Yeah.
My question is, if you, for instance, if you have, let's say 10 or many algorithms and you have like one parameter for each of these algorithms, does it change much? It's pretty the same in terms of complexity. That's my question.
Okay, so that's a good question. So first of all, I should mention in the concrete example that I spoke about today, I picked for the clustering, we are trying to learn the linkage criteria and also we are trying to learn the distance criteria. We only have a small number of parameters. I chose them so that I can give kind of insights in the proof, right? But in our work, we also look at cases where we have many more parameters. So for example, like for the clustering example, actually one concrete extension for the clustering example, if you are trying to interpolate not only between two distance functions, but if between a number of base distance functions, you might have capital N of n, and n is large. You can still adapt the analysis, and the similar analysis goes through, except now these dual functions, where you fix an instance of the parameters, they're of course multidimensional. So the techniques still apply to such multidimensional cases for clustering, and we have other examples like pricing problems and sequence alignment problems, right? So we can apply techniques to the cases where the algorithm's family is parameterized by many parameters. It's one answer. Now you're asking also, maybe your question also hinted towards a different question, which is, what if I have kind of different types of algorithms family and they all have parameterized by many parameters? What can I say then, right? Can I still give generalization guarantees, right? And maybe I have not only one type of algorithm kind of that is parameterized by many parameters, but maybe I have several different types of algorithms parameterized by different algorithms, and I'm still trying to learn the best algorithm from this union of family of algorithms. And we have not done this we have not written down details in this direction, but I think the answer is that we should be able to extend the techniques, just because in learning theory, when you analyze pseudo dimension, there are composition results, right? For example, we know that the pseudo dimension of union of two classes, double bonded, can be written as a function of the pseudo dimension of each of the individual class. And so based on composition results from learning theory, I think we can also handle that extension, where you have not only one family of algorithms parameterized by many parameters, but several very different families of algorithms parameterized by many parameters, and you are still trying to learn the best of them.
Thank you very much.
Sure.
Okay. I promised that was the last question, but I have one more. I'm interested in knowing how is the theory versus practice game in this area. I mean, are there, for example, algorithms that you cannot use because they have too many discontinuities that beat your combination of well-behaved algorithms, or maybe said another way, the guarantees that you obtain, do they turn into actually better performance always, or there are ill-behaved algorithms that in practice perform better anyway, as it happens in other areas?
Okay, so it's a great question. So for some of the examples, like for clustering problems, so like the one that I mentioned, when we learned the linkage criteria and the distance function, there we have, like, of course, we started with some, initially looking at, like, what can you say theoretically? We had the Call 17 paper, then we had the sequence of papers, right? But, they are more theoretical, looking at sample complexity, and, and the underlying algorithmic problem was maybe we didn't know quite how to solve it, but there it's a success also from a practical point of view, because we have a recent IQPs paper where we're also showing how, we can exploit the structure that we developed, where we analyze in order to get the sample complexity guarantee to also kind of find an efficient meta procedure for learning the best algorithm from the family. So there it was a success all the way from theory to practice. It started from practice because the family of algorithms were looked at were motivated by practical considerations, and we provided good theoretical guarantees, but it took us a number of works, like 2-3 papers, to then eventually use our use our insights, the structure results, to then also give an efficient meta procedure for learning the best algorithm from the family. And there we show experimentally on large scale data sets that are common in machine learning that we do better than what was known there before in practice, like significantly better. So that's nice. That's a success story. But then we also have some other results, like, for example, learning to like for solving mixed integer programs. We're looking at branch and bound techniques, which are widely used in artificial intelligence, where and there we have sample complexity guarantees. We have an ICML18 paper. We do have sample complexity guarantees. And we have some even more recent one, actually. But there we're not quite able to answer your question. Like, there we know that in principle, it's better to do better than people are doing currently in practice, and have experiments showing that. But we don't have yet quite an efficient algorithm for somehow learning the best branch, the best algorithm from our family, right? That we can show that scales up yet. Okay, so there the specific parameterized assembly of algorithms we are looking at. We're trying to, the parameter is like for branching rules. There are many ways to branch, right? And then which variable should you branch on? Well, there are many heuristics. You can try to put down a parametric family that combines many heuristics. You get the parametric family of branching rules, and then we have results showing kind of the sample complexity of this question. How can you learn the best branching rule that leads to the smallest tree, the best running times for your type of instances, right? Then we have great sample complexity guarantees, and also there we show kind of that in principle, we should be able to do better than what people are doing currently in practice. Because for example, in that case, we show that if you just put down a discretization of the parameter space, that doesn't work, because for any fixed a priori discretization, you might do really badly, because it could be kind of just good pockets of kind of parameters that you're never going to catch in your discretization. So the discretization shouldn't be data independent, right? If it's data independent, you are doomed. We show that formally. So we show that we have potential to do better than what people are doing currently in practice, but sample complexity guarantees, we don't have efficient procedures for doing that. So that's an example where I think we can work more to go and improve on what people are doing in practice. But I think if we continue and if we are successful, we can have great impact, right? Because, for example, commercial software like Cplex and so on, they have many parameters that people are these days tune by hand. So it's great to try to use kind of machine learning and instances of the problem coming from the domain to tune them automatically. So I think that's a great example of a problem where we don't have yet efficient algorithms to really do the tuning automatically, but we know that in principle, we should be able to do better than what people are doing currently intuitively in practice. And we also know that if you just say by intuition, you can do really badly. So you kind of have to do something smarter.
Okay, thank you very much. Well, thanks, Nina, again for that great talk. And thanks. Okay, so this finishes the session of the plenary lecture now.